All right, in this video, we're going to talk about some matrix operations. We're going to talk about addition, subtraction, multiplication, and then the matrix vector transpose. Let's begin by first talking about matrix addition. So let's consider the two m by n matrices A and B respectively. We can concisely represent their addition by the following formula. If we extend this out to two simple 2 by 2 general matrices, we can see that all we're doing is adding the corresponding entries. So going through this process for each column, we end up with these results little c, which we'll use as the components for our resultant matrix big C. So what we end up with is this addition of these two matrices, which yields a new resultant matrix big C. Now if we interpret the columns of these matrices as simple column vectors, we can perform basic vector addition on these and interpret them geometrically using this simple tail to tip method as I've animated here. Finally, let's go over a simple example as such. Let's now look at matrix subtraction. So let's once again consider two m by n matrices A and B. Now one thing that I should mention now is as far as addition and subtraction goes for matrices, the two corresponding matrices must be the same dimension, meaning they need to either be square or rectangular. You cannot add a rectangular matrix to a square matrix, which is why I specify here that both A and B are m by n. Let's continue. Similar to addition, we're going to simply go component-wise throughout the entire matrix, and it's going to be the exact same process. Of course, we're now just taking the negation of that. Once again, as we go through all these operations, we're forming these little entries C, which will be used to fill up our resultant matrix big C. And then as we can see again, we end up with the following result. Similarly, we can geometrically interpret this as the negation operation of vector addition. So we might notice a pattern that most of these vectors are switching directions. Finally, let's look at another simple example. Let's now look at matrix multiplication. So let's consider the following m by n matrix A and the following n by p matrix B. Now we can formally describe their multiplication from the following sum formula, but let's try to visualize this a little bit better with this simple demonstration. So in multiplication, what we're looking at is going row by column. So we want to multiply the first element of the first row by the first element of the first column. And then we want to follow this similarly for the second element. And what we do is we go first row, first column, first row, second column, second row, first column, and we finish with second row, second column. This is the structure that you should keep in mind whenever you're multiplying matrices. And what we end up with, of course, is this resultant matrix C composed of these resultant elements, little c. Let's look at this numerical example. So we go first row, first column to get 5. Now we're going to have 1 times 0 plus 3 times 5, which will give us 15. 2 times 2 plus 4 times 1. Which give us 8, and then 2 times 0 plus 4 times 5, which will give us 20. Now that we have these elements, we can construct our resultant matrix C, being 5, 15, 8, and 20 respectively. Next, let's talk a little bit about dimension as far as multiplication goes. In addition and subtraction, we needed to make sure that the dimensions of both matrices match exactly. Meaning we can add two square matrices or we can add two rectangular matrices, but we can't add a square matrix to a rectangular matrix. In multiplication, this is slightly different. What we're interested in ensuring is that the number of columns in our first matrix, in this case A, match with the number of rows in our second matrix, B. So A is m by n, meaning it has m rows and n columns, and B is n by p, meaning it has n rows and p columns. So we see that the number of columns in A match with the number of rows in B, so we know this is a valid multiplication. Now that we know that, let's consider what the dimension of our resultant matrix is after actually performing this multiplication. So this would be a new matrix, either A, B, or we can call it C. And what we're interested in is making sure that it's dimension rows of A by columns of B. In this case would be M rows in A and P columns and B. So we end up with a matrix that is M by P. Let's move on. The next thing I want to mention strictly is that matrices do not commute in general. Let's now try to get some basic visual intuition. This animation will make a lot more sense when we talk about linear transformations, but I thought I'd include it if it helps some of you. Let's now look at the matrix and vector transpose. So the transpose of a simple column vector simply turns it into some row vector, V transpose. Now the same logic applies for matrices. If we take some matrix A and want to consider its transpose, we simply take all the rows of A and turn them into the columns of our new matrix A transpose, as shown. Now some key properties to keep in mind for matrix transposes are the following. If we take the transpose of the transpose, essentially, we just end up with the original matrix A. If we take the transpose of the product of two matrices, we can also rewrite this as B transpose A transpose. And if we take the transpose of alpha times A, where alpha is just some scalar, we simply end up with alpha A transpose. Now we can get a lot more in depth about the transpose, which you probably will later, but a nice way to think of it is that we're just changing the structure of our object. That's all I really have for this video. It was supposed to be short and sweet, but next video we'll talk about the LU decomposition, which we'll need multiplication for. So thanks for watching, and I hope this was helpful for some of you.